3 seconds ago, according to real quantum physics, another version of you made a different choice, and that choice became its own universe. Not a metaphor, not a thought experiment, a direct prediction falling out of the same equations that built every microchip and laser on Earth. That other universe is not somewhere distant. It branched from the same quantum event you just experienced without noticing. What happened to that version of you in the moments that followed is the question this video was built to answer. The equation at the center of all this is called the Schrödinger equation, and it describes how quantum systems evolve over time with perfect, unbroken logic. What it does not do is tell you which outcome you'll see when you look. It tells you that all outcomes continue to exist simultaneously. Most physicists spent decades assuming something outside the equation collapsed that blur of possibilities down to a single result. But the equation itself never collapses. And a growing number of physicists think that silence is the answer. If nothing in the math forces a single outcome, then every outcome is real, playing out in a branch of reality you can no longer reach. The universe you're sitting in right now might be just one thread in something far larger than anyone has ever been able to measure. Forget the portal, the mirror dimension, the evil twin with a goatee. Real physics has something stranger in mind. Parallel universe, in the physicist's definition, isn't a place you travel to through a wormhole or a crack in space. It's a branch of reality that split off from yours at the moment a quantum event landed one way instead of another. No dramatic rupture, no visible seam. Just a single particle settling into one outcome while another version of the same moment quietly continues somewhere else. The science fiction version asks you to imagine crossing over, but the physics version says you never could, because the branches don't touch. They don't share light or gravity or any signal you could ever send or receive. What makes this genuinely unsettling isn't the scale of it. It's how small the trigger is. One electron, one quantum coin flip, and the universe you're sitting in right now is just one answer out of many. So why did serious physicists start treating this as more than metaphor? The equation that describes quantum reality never actually tells a particle where to land. It tells you every place it could land simultaneously. That spread of possibilities is called the wave function, and in the lab, it works with breathtaking precision. But the math contains a problem that physicists have argued about for nearly a century. When you measure a particle, the wave function appears to collapse. All those possibilities vanish except one, and reality snaps into focus. The question that haunted Hugh Everett in 1957 was simple and devastating. What if it doesn't? What if the wave function never collapses and every possible outcome actually happens? Everett's answer was the many worlds interpretation. And it wasn't a philosophical flourish. It was a refusal to throw away the math. If you take the equations completely seriously without adding any collapse rule, they describe a universe that branches at every quantum event. Every measurement, every interaction, every fired neuron in your brain splits reality into versions that never meet again. The same equations that predict atomic structure with 11 decimal places of accuracy also seem to predict you, plural, multiplying across an infinite tree of diverging worlds. Physicists can't dismiss many worlds because dismissing it means dismissing the math. And the math is the most tested theory in human history. Many worlds is only the beginning, because quantum mechanics isn't the only framework that keeps arriving at parallel universes. Cosmologists studying the early universe ran into the same problem from a completely different direction. When the universe was born, a process called inflation stretched space faster than light could cross it, and that process never fully stopped. In most models, inflation keeps churning in distant regions of space, spawning new universes the way a foam spawns bubbles, each one sealed off, each one potentially different. String theory adds another layer to this picture, because its equations don't produce one unique universe. They produce something like 10 to the power of 500 possible versions, each with different physical laws. That number is so large, it makes our entire observable universe look like a rounding error. And then there's the most radical proposal of all, that every mathematically consistent structure doesn't just describe a universe, it is one. What you're left with isn't a single fringe idea, but a recurring answer that keeps surfacing across independent branches of physics, which raises the harder question of what those other universes would actually look like from the inside. Those bubble universes aren't all strange and distant. Some of them might be almost embarrassingly close to this one. A branch where you ordered tea instead of coffee this morning still has stars, still has gravity, still has a version of you reading the same news. The differences compound slowly, like a river that splits and drifts apart over miles rather than instantly. But push further out along the spectrum, and the divergence becomes something harder to hold in your mind. In universes where the fundamental constants land just slightly different, hydrogen never bonds, and the first stars never ignite. No stars means no carbon. No carbon means no chemistry. And no chemistry means the darkness is genuinely, permanently empty. You wouldn't be different there. You simply couldn't exist in any form, not even as scattered atoms. That's the real weight of the multiverse. It doesn't just multiply versions of you, it erases you entirely in most of the space it describes. So the question that matters isn't whether other universes exist, it's whether any of them are close enough to carry someone who is recognizably, specifically you. Every quantum event inside your body right now is splitting the branch you're standing on into new ones. Not occasionally, constantly, in every cell, in every firing neuron, in every photon your retina absorbs from this screen. The version of you who blinked a half-second earlier already lives in a different world than the one listening now. Multiply that across every particle interaction since the moment you were born, and the number of branches carrying some version of you isn't large. It's beyond any number language was built to hold. Most of those versions are nearly identical to you. Same face, same voice, same coffee going cold on the same desk. But the branches don't stay close forever, because small quantum differences compound the way interest does, quietly and then all at once. A few branches out, that other you made a different choice at a moment that mattered, and the lives have since grown unrecognizable to each other. Further still, and the divergence is so total that calling them you feels like a courtesy rather than a fact. What you're left with isn't a twin somewhere, it's a tree. And you are only the branch that happens to be doing the looking. Whether any of those other branches could ever send a signal back is the question that separates philosophy from physics. If another universe exists right now, the question isn't just philosophical. It's whether physics can ever reach it. The most promising lead comes from quantum mechanics itself, where interference patterns suggest particles are somehow sampling paths we never directly observe. Some physicists argue those patterns are the shadow of other branches pressing against our own, a faint structural fingerprint left by worlds we can't enter. The boldest experimental target is the cosmic microwave background, the oldest light in the universe, a faint glow that maps the sky in extraordinary detail. If our universe once collided with a bubble neighbor during cosmic inflation, that impact should have left a scar, a cold bruise stamped into that ancient light. Cosmologists have searched that map carefully, and so far, nothing confirmed. The absence isn't a refutation, it's a constraint, which is a very different thing in science. Every null result tightens the boundaries of where another universe could be hiding and how it could have touched ours. You're left with a sky full of data, and a question the data hasn't answered yet. What physics can actually agree on, and what that silence might mean, is where this ends. The honest answer is that no experiment has confirmed a parallel universe. Not one, not ever. What physics has confirmed is stranger. The equations that describe our universe don't stop at its edge, and they don't forbid what lies beyond. The multiverse isn't a fantasy physicists entertain to feel bold. It's a residue left behind when the math is taken seriously. Every version of the theory, from branching quantum worlds to the infinite expanse of eternal inflation, carries the same uncomfortable weight. They might all be true, and we might never know. So what does that leave you with? If another version of you chose differently at some moment that mattered, chose to stay or leave or speak, that choice still defines you here. You are not every branch. You are this one, under this sky, carrying exactly the choices that made you.